Hyper-deterministic exploit analysis of remote lane assist manipulation. A comprehensive analysis of potential remote control vulnerabilities in modern vehicle lane assist systems. Modern vehicles are increasingly integrated with advanced driver assistance systems, including lane keeping assist, lane departure warning, and autonomous driving systems. These systems rely on a combination of cameras, radar, ultrasonic sensors, GPS, LiDAR, and AI-driven decision-making to control vehicle steering with minimal driver input. However, as automotive technology becomes more dependent on software-controlled electronic systems and remote connectivity, the possibility of remote hijacking, signal manipulation, or cyber warfare targeting these critical vehicle functions grows exponentially. This report provides an exhaustive analysis of how lane assist could be remotely controlled, detailing the attack vectors, cyber vulnerabilities, wireless interference methods, hardware exploitation techniques, AI manipulation strategies, and real-world threat scenarios associated with this emerging security risk. Before examining vulnerabilities, it is crucial to dissect the fundamental components of a lane assist system. Modern lane assist systems rely on the following critical subsystems. Front-facing camera module mounted near the rearview mirror or windshield. This camera detects lane markings and vehicle positioning. It utilizes AI-driven image recognition algorithms to differentiate between lane boundaries, road edges, and objects. Often uses infrared sensors for low-light performance. Electronic power steering system receives signals from the lane keeping assist control module and autonomously adjusts the steering angle. Uses torque vectoring algorithms to apply corrective force if the vehicle drifts. Integrates with adaptive cruise control and collision avoidance systems. Radar and LiDAR sensors, measures vehicle distance from lane markings and detects obstacles. Works in conjunction with GPS positioning to estimate vehicle drift and alignment. Provides redundancy for camera-based lane detection. Vehicle-to-everything communication connects vehicles to cloud servers, other vehicles, infrastructure, and external control servers. Utilizes 5G, LTE, DSRC, and satellite networks for real-time data transmission. ECU processes all input data from sensors, cameras, steering control modules, and remote updates. Can receive firmware updates remotely via over-the-air update mechanisms. Alright, so let's dive into the attack vectors and explore how lane assist could be hijacked remotely. First up, we have wireless and remote exploits. Remote attackers could manipulate lane assist systems via wireless cyber intrusion, signal interference, or even cloud-based command injection. Now let's talk about over-the-air firmware manipulation. Modern vehicles receive remote software updates via 5G, LTE, or Wi-Fi, allowing manufacturers to improve functionality. However, attackers can exploit OTA update servers or use man-in-the-middle attacks to inject malicious firmware, altering lane assist behavior. A compromised firmware update could reverse steering polarity, making the car turn opposite to corrections. It could also increase steering sensitivity, causing dangerous overcorrections, or disable driver override, preventing manual control. Moving on to cellular-based remote exploits. Many modern vehicles connect to cloud servers for navigation, diagnostics, and software management. An adversary with access to these cloud servers could inject malicious control signals into the vehicle-to-everything infrastructure. This would allow them to override lane assist commands, issue false lane correction signals, forcing vehicles into oncoming traffic, or disable safety limits, preventing corrective steering intervention. Lastly, let's consider Bluetooth and Wi-Fi exploitation. If the vehicle's lane assist system integrates with the infotainment system, an attacker could exploit Bluetooth or Wi-Fi vulnerabilities to gain indirect access. A zero-click Bluetooth vulnerability, like the Blueborn exploit, could allow an attacker to execute commands without any user interaction. In addition to remote hacking, direct physical manipulation of sensors and inputs can be used to control a vehicle's lane assist system. Lane assist relies heavily on AI-based lane recognition via a front-facing camera. Attackers could deploy projected light patterns or AR-based road overlays to trick the AI into detecting false lane markings, force the vehicle to correct in unintended directions, or create phantom lanes leading to collisions. Vehicles often use GPS-based lane correction in conjunction with camera input. By spoofing GPS coordinates, attackers can override lane assist positioning data and cause false corrections toward off-road areas, or deactivation of lane assist in critical moments. A well-placed RF jammer or EMP device could disrupt steering control feedback loops and lane assist sensors by flooding their frequency spectrum. An EMP burst could disable steering interventions, making the driver lose control. Lane assist uses deep learning models trained on road images to recognize lanes. Attackers can inject adversarial AI samples into the model dataset to cause lane confusion in specific conditions like rain or low light, or false edge detections leading to vehicle drift. Vehicles using AI-driven self-driving neural networks are vulnerable to malicious neural network reprogramming and backdoor triggers that activate steering anomalies under preset conditions. Hostile actors infiltrate V2X cloud systems, sending lane assist override signals to all affected vehicles on a major highway. Vehicles begin self-correcting into oncoming traffic or barriers, leading to a massive pile-up due to AI-driven chaos. A targeted attack on a specific high-value target's vehicle via a personalized firmware exploit. Lane assist subtly shifts the car toward guardrails or oncoming traffic, making the attack appear to be a technical failure and eliminating suspicion of foul play. Nation-state actors disable lane assist on all vehicles in enemy territory, leading to road chaos. This form of cyber warfare disrupts supply chains and civilian mobility. Lane assist systems, while designed for safety, introduce massive cyber-physical vulnerabilities when remotely accessible. Attackers could manipulate firmware updates, override lane correction commands via cloud servers, exploit AI models to introduce false lane detections, or deploy GPS or sensor spoofing to manipulate vehicle trajectory. As AI-driven automation increases, these risks must be addressed before real-world exploitation occurs. White Hat Vanguard, Securing Tomorrow Today, Jeff Logue, SM, CD Cyber Espionage AI, Red Team Strategic Analyst and Innovator.